Welcome to my presentation on the math behind the electronic brain, also known as the artificial neural network. I will be focusing on the gradient descent and backpropagation algorithms, specifically on gradient descent, which is used to optimize. And my name is StevenVeld. I'm a representative from Math 260 Honors, and my mentor is Professor Zika Perovich. Quick note, don't get too attached to the abstract if you happen to read it in the showcase program, because unfortunately I did have to cut out a few things for time's sake. Alright, so brief history of artificial neural networks. They can be traced all the way back to the origin of the computer with Alan Turing in 1936, also known as the Turing machine, and he liked to call it the electronic brain. That's where I got the idea for the title of this presentation. And the history of ANNs can be traced back, like I said, starting with computers, which eventually developed into artificial intelligence. Combine this with knowledge of the brain, and that gives us artificial neural networks, which were first proposed by Warren McCullough and Walter Pitts in 1943 to 1944. And as I mentioned, they're modeled after the brain. So basically, we've got a bunch of digital neurons organized into layers, and every neuron in one layer is connected to every neuron in the next layer, which is once again modeled after the brain and allows us to have a multitude of stored information, and also allows for learning, which is one of the main benefits of artificial neural networks. Some other important benefits as compared to regular artificial intelligence is fault tolerance, as the complexity allows them to work with imperfect information, and also allows them to deal with complex and nonlinear problems. Additionally, because we have many neurons in each row, it allows for parallel processing. And lastly, the distribution of data throughout the system rather than in one database allows for distribution of risk. So briefly describing machine learning here. So there's three main categories: supervised, unsupervised, and reinforcement learning. I will be focusing on supervised machine learning, which in itself has two categories, classification and regression. Basically, the way that supervised machine learning works is that we provide the machine with both the inputs and the expected outputs. So one example of this would be we provide it with a bunch of pictures of faces, and the expected outputs are we tell it which emotion this face has, and we're trying to get it to be able to predict emotion based on pictures. So the way it learns is it just approximates it over and over again by running this algorithm, and over time improves, which we'll be getting into later. That is the focus of today's presentation. And basically these other two categories aren't as, are still very important, but we will not be focusing on them today. Alright, so getting into supervised machine learning, basically the way it works is we have two steps. We have the feed forward and the feedback, also known as propagation and backpropagation. So basically we start by encoding one of the many inputs in the training set, so for example a picture, like I was mentioning from earlier, as a sequence of numerical inputs, and this is our input layer. Now, as I said earlier, every single neuron in the input layer is connected to every single neuron in hidden layer 1. So we have a lot of connections, and each of these connections has a corresponding weight, and this represents the strength of the connection. And basically, for each neuron, we will multiply every single input that is being attached to it by the respective weight, and then we'll add this thing called a bias, which is sort of just this artificially induced, addition, just to make things run more smoothly. Then we'll take this new input, run it through an activation function, the most common being the rectified linear unit, also known as ReLU, which we won't be getting into. And then we repeat this for each layer using the outputs from the previous layer as our new inputs. So basically, we eventually get to our output layer, which we can then compare to our expected output using a cost function, the most common being the mean squared error cost function, also known as a quadratic cost function. And what this does is it basically just tells us the error or the disparity between our actual output and our expected output. Now, obviously, we want to minimize our error, and we do this using our gradient descent optimization algorithm, which makes use of another notion from calculus called partial derivatives, which we acquire using backpropagation, which unfortunately I will not be getting too deep into today because it has some heavy math involved, especially the chain rule. But that's another interesting and important concept. So the last thing we do once we've optimized this algorithm is we run this new and improved algorithm on a test set to check for overfitting, basically just making sure that we haven't overfit our data to the training set, and it's still able to generalize to other data that we want it to be able to do. So I was talking about gradient descent. Before we get into that, we need to explain the gradient, which is an important tool from calculus. So the gradient, del f, this triangle symbol, we say del, is the vector of all partial derivatives of the function f. Now basically, sounds pretty simple, but it actually has some very, very nice and important properties, and I'll briefly derive them here. So we'll start with the notion of the directional derivative. The directional derivative is just the dot product of the gradient and the direction that we are going in, which we call the vector u. The dot product just means that we are multiplying corresponding components, so if each have the same amount of components, we can just multiply corresponding components. The directional derivative represents the slope of f in the direction of u. So as we can see here, we take a vertical cross section of it, we go in that direction, and the directional derivative represents the slope. Now, basically, another important formula from calculus is this right here that says that the dot product of two vectors is equal to their magnitudes times the cosine of the angle between them. Now, this is derived using the law of cosines, which I won't be getting into, but just a brief side note, I think it's really it's really cool and beautiful to be able to see how we have all these things building on top of each other, eventually leading us to really complex and very useful algorithms. I don't know, that's just me. I like to see that. But anyway, so based on this formula right here, we can see that the directional derivative, or del f dot u, is at its maximum when cosine of theta is equal to 1. In other words, the angle is equal to 0, meaning that the gradient is the same direction as the directional derivative. And it is minimum when the cosine is -1. In other words, the gradient is in the opposite direction of the directional derivative. Now, this is very important because this leads us to the properties of the gradient. Del f points in the direction of steepest ascent because, as we can see, when we are going in the same direction as the gradient, that means that we have the greatest directional derivative, and negative del f points in the direction of steepest descent, analogously. And this right here is very important because this is what we use for gradient descent. So gradient descent, in this context, c represents the cost function we want to minimize with respect to weights and biases, and del c, instead of del f, it represents the partial derivatives for all weights, and we can also do the biases analogously. So a quick analogy just to give you a feel for how gradient descent works. Basically, imagine you're standing on a foggy mountain and you want to get to the bottom of the mountain, but you can't see where it is. All you can see is right in front of you, so you're like, okay, well, if I want to get to the bottom, I just step in the direction of steepest descent. And you continue doing that, and you continue going farther and farther down until you reach a valley, or a local minimum, we call. And that is basically how gradient descent works, and I actually just explained what's going on here, even though this might look sort of weird and mathematical. But basically all this is saying is that you have your current position, right, where you're standing on the mountain, which can be represented by the vector of all the weights. You have your gradient, which is the direction of steepest ascent, right? And obviously you want to go in the opposite direction, which is why we have this negative sign here. And all we're saying is that we have this little small constant learning rate because we don't want to step too far in that direction because the gradient might change as we go in that direction, as it's constantly changing. So we don't want to overstep. So all we do is we step a little bit in that direction, and that gives us our new weights. And then we just repeat that using these new weights over and over until we converge to a minimum, which would be the valley, or the bottom of the mountain. Now, obviously, this only leads to a local minimum, and there are certain techniques to give us global minima, which we'll get to in a bit. But it can't be perfect, unfortunately. Just some quick terminology. One epoch represents one pass through a training set. And we will use this in describing the three types of gradient descent: batch, stochastic, and mini-batch gradient descent, which is the most common. And a quick note before we move on to the next slide. The reason that we use gradient descent, which is a local iterative optimizer, is because conventional global techniques for finding global minimum are incredibly computationally expensive with so many variables, because we would have to calculate the derivatives of these variables across the entire function, which would be very difficult. All right, so our first type is batch. Basically, the way this works is, this one is possibly the most intuitive. We basically just calculate our vector, our gradient, for a single training example, and then we do this for all of our training examples using all of the weights and biases in there, and then we average this gradient across the entire training set. Then using this gradient, we then take a small step in that direction, and we repeat that over and over again until we converge to a minimum. So the advantage of this is because we are basically doing many computations at once, we can vectorize it, which basically means that we're just performing many computations at once, which allows us to increase the efficiency and speed of our convergence, along with the fact that it is more stable because we are taking averages and a less quote-unquote noisy convergence. However, a stable convergence can actually be an issue as well, because skipping down to our disadvantage here, it means that we cannot escape local minima, because if it is so stable, when we reach a local minima, there will be no fluctuations to sort of help us jump out of it, in a sense. The other issues are that the entire data set might not fit in the memory, which would just sort of destroy the whole thing. And it's also very slow, because we have to calculate gradients for the entire data set just for one update, which takes a lot of computation. So to solve some of those issues, we also have stochastic gradient descent. So the difference with this one is that rather than calculating the average of the gradients over the entire training set, we calculate the gradient for one training example, and then we update the parameters with that example. And we go through all the examples, and then we shuffle it randomly and do it again and again. And the reason this works is because in a lot of training sets, a lot of our examples will be very similar. Going back to the pictures of faces one, we might have a lot of mad faces that look very, very, very similar, and it would be redundant to calculate the gradient for all of these and then average them, rather than doing it every time individually, because we just get to move farther in that direction for the same cost. The other benefit of this is that the fluctuation helps us escape from local minima. Essentially, if you think about it, because we are not taking the average, and every single training example might have a different cost function, what this means is that on the big cost function, on the average cost function, each little step we're taking isn't actually going to be in the direction leading to a local minima, but overall they will end up getting us possibly to an even better local minima, because these fluctuations can help us escape the local ones and then continue heading downward. And the last thing is that it uses less memory, obviously, because we're only storing one example at a time. The disadvantages, once again, we have the flip side of the fluctuation, in that it complicates convergence, although decreasing the learning rate can help, as we will basically start taking smaller and smaller steps over time. And lastly, the fact that there's no vectorization, because we're only doing one example at a time, and the frequent updates, which take a lot of computation, leads to heavy and slow computation. So this on its own is not very feasible either, which is why we have our third and most important type, mini-batch gradient descent. It is the most common. It's also often called SGD as well, just for brevity. And in this one, in one epoch, we randomly shuffle the training set, as we did with stochastic, but then we update the parameters for each mini batch of n training samples. So usually the mini batch is between 50 and 256 training samples, and this basically just gives us the best of both worlds. We get a convergence that's relatively stable, but there's still enough fluctuation to escape local minima, because we're basically somewhere in between the two, and we get the efficiency of vectorization, but it still fits in memory, and we can see all of that here. And basically, there are many variations of mini-batch gradient descent, because there are still challenges that need to be faced, and this is just a great example of ideas building on top of each other. But unfortunately, we won't be able to get into these today, because it is incredibly complicated. So as you can see, I've sort of made this slide red just to show you that yes, this is still something that exists, and if you happen to have questions about it, please feel free to ask. But unfortunately, we won't be getting into that today. The other thing we will not be getting into is the chain rule and backpropagation. Once again, just an important notion from calculus that allows us to actually acquire all these partial derivatives that we used in gradient descent. But once again, unfortunately, just not enough time for this today. So we'll just fast forward through all of that. Anyway, for our overview, basically, artificial neural networks are incredibly powerful because they work like the brain, and biology is one of the most powerful things out there. We've got a bunch of applications, from image compression to language recognition to financial forecasting. They learn through gradient descent and backpropagation. And once again, I just want to emphasize the amazing concept of all these ideas building off of each other. And this is our bibliography. If you want to look at a good example application to image processing, take a look at source 4. If you want to take a look at the thorough proof of stochastic gradient descent escaping local minima, take a look at source 2. And that will be all for today.